ನೀವು ಮ್ಯೂಟ್ ಮಾಡಿ ಅಲ್ಲ ಸರ್. ಇಲ್ಲ ಇಲ್ಲ, ಓಕೆ ಓಕೆ ಇದೆಯಲ್ಲ. Hello, sir.
Hello.
Sir, can you hear me?
Yeah, definitely.
Okay. Thank you, sir. Thank you.
I am ready.
Okay.
Namaste, sir. Namaste.
Hello, sir.
Hello, sir.
How are you?
I'm fine, sir. Thank you.
Very nice. Very nice to see you.
And thank you, sir, so much.
Yeah.
Thank you for giving the
pleasure
opportunity
interact
to
with you.
Yeah.
It's a pleasure to interact with you.
Oh, thank you so much, sir.
Yeah.
It's my pleasure, actually. Namaste, sir. Hello, sir.
How are you?
I'm fine, sir. Thank you.
Very nice. Very nice to see you.
Thank you, sir, so much.
Yeah.
Thank you.
Hello.
Hello.
Hello. Good afternoon, all of you. I welcome you to the international webinar on nanomaterials and robotics, hosted by Raja Lakamagoda Science Institute, Belagavi. I now hand over the session to Professor Vadgavi, Head of the Department, Physics and Electronics, to address the welcome speech to the gathering. Over to you, sir.
Thank you. Good afternoon to everyone. It is my proud privilege to be in front of you to welcome. First of all, I am very happy to welcome Dr. V.D. Elamali, Principal, Daily Societies, Raja Lakamagowda Science Institute, Belagavi. Welcome, sir. I extend my warm welcome to the guest speaker, Dr. Basargowda Patil, Team Leader, R&D, Read Print Technology, Queensland, Australia. I'm also happy to welcome all the participants who have shown overwhelming response to this webinar. I also welcome all my colleagues and student friends. Once again, welcome to one and all. Thank you.
Hello.
Hello.
I request our beloved principal, Dr. V.D. Elamali, sir, to address the gathering. Over to you, sir.
Good afternoon, one and all. And good evening, Dr. Basargowda Patil.
Yes, sir. Good evening.
It's a great pleasure once again in a week's time welcoming participants and invited speakers for webinars the KLE Society's Raja Lakhamgowda Science Institute is conducting. As everyone knows, 7 stars, the teachers built KLE Society way back 103 years. It is indeed our privilege to work in such an institution built and brought up by the teachers and led by an eminent visionary, present chairman, Dr. Prabhakar Kore. During centenary celebrations, the work contributions made by the present chairman, Dr. Prabhakar Kore, was overwhelmed by the participants and the contributors, donors, and supporters, and they called him by name Eighth Rishi of KLA Society. It is an honor to work under him, and his vision is a very, very encouraging boon for the further development of KLA society. In the same line, in 1935, Raja Lakhamgoda Science Institute was established as an offshoot of Lingaraj College. This science institute, over 85 years plus, has grown with its own speed and enthusiasm by the support of directors, well-wishers, students like Dr. Basangoda Patil, and the teaching faculty with their dedicated service for the betterment of education in this part of Karnataka. To continue the same zeal, Raja Lakhamgoda Science Institute, since 2010, is working under autonomous mode, and it is contributing in its own way for the betterment of faculty and students. In the line, today we are organizing an international webinar on nanoscience and robotics. It is a wonderful subject. Although being a teacher, I can't teach at a nano size, but I can understand its depth and its very much initial inclusion in teaching and learning method. Of course, in the present scenario of COVID, robotics is of a greater help because of spreading infections, treating patients. Robotics plays a vital role. Thus, hats off to those who invented robotics and to the scientists who are working relentlessly to build nanoscience as the future technology. It is indeed a great pleasure to select such a nice subject from the Phrygic fraternity of our institution. I once again welcome all of you for this webinar. Please enjoy the session. Thank you one and all. Over to
Thank you, sir. Thank you so much for your address to the gathering. And I now would like to introduce our guest speaker, Dr. Basanagoda B. Patil. It's my proud privilege to introduce this speaker. He has completed his BE in ENC from Vishwesvaraya Technological University, MTech in Industrial and Management Engineering from IIT Kanpur. He initiated his research career with fellowship received from King Abdullah University of Science and Technology, Saudi Arabia. Then he further received fellowship for his PhD from Queensland University of Technology, Brisbane, Australia. His PhD topic was enhancing the electrical performance of donor acceptor type polymers through device engineering for electronic applications. During his PhD tenure, he has worked as research intern in Research Center for Organic Electronics at Yamagata University, Japan. Presently, he is placed at Reed Print Technologies as a team leader in R&D division in Brisbane, Queensland, Australia. We have a pleasure to you have, sir. We welcome you wholeheartedly to this session, and over to you, sir.
Yeah. Namaste, and thank you for the kind invitation and all the efforts and introduction. Very kind of you. I'm personally thankful to Principal Sir V.D. Valmalai and Dr. S. Kavlekar, Shri Vadagavi Sir, A.S. Pujar, and Dr. Vinay Kumar for all the motivation and support throughout. So without further ado, I will share my screen and we shall start the presentation. So I hope the screen is audible, visible now?
Yes, yes, sir. Yes. Go ahead.
Okay.
Thank you.
So as introduced, we will be dealing with nanomaterials and robotics is the topic. So in this one, we will be, first of all, try to understand the introductory part, like what they actually mean and how they have been progressing throughout. And then we will particularly go for the better understanding what is this nanomaterial, how to comprehend it. And in that particularly, when we apply that nanomaterials to the technological platform, how it becomes a technology. And then in that particular importance is the transistor. As you all know, even in the case of conventional electronics, the transistor was the main device based on which all the circuits and all the embedded systems, all the circuits have been formed. So even in this particular case of nanomaterials and nanotechnology, that becomes a base platform on which all the devices and circuitry will be built towards the nanorobotics. Then we will see what will be how this kind of sensors and all these stuffs will aid the process of nanorobotics, which will be fighting some of the most critical diseases of this world, or they might be used for various applications, which only the time is going to say. We will just touch upon those things as well. And then if you all have any questions, please feel free to ask me and make a note of those questions so that I will be able to address them, or you all can send it in the chat so that they will be segregated and we will be able to address them. So initially, let us start with the introduction. And the main important thing is the nanoelectronics or nanomaterials are different from the conventional materials. This is the reason why they have more, they can be transparent, they can be flexible. If you see a typical silicon, which has a 4 valence electrons and all these possibilities, so it has its own applications. It has a high mobility. The mobility is almost 1400 centimeters square per volt second. But that kind of speed might not be necessary and essential for all the applications. There are so many applications in this world which doesn't need that kind of high processing labs. For example, the silicon, if you see in India, there are not much silicon fab labs we have. It's just because of the expenditure which might involve in those silicon-based manufacturing equipments. But the flexible electronics and nanoelectronics and nanotechnology basically gives us the scope that it will be very low cost production, and it can has its own applications. As you can see in this photo here, the Bayer is a material science department which has come up with inks, and those inks have been printed on those lines, and they are conductive, and they are functional. Making those materials functional was a big deal, and people have been able to do the research and get it done. We will see how the things have been progressed. If you see that the future is all about nanoelectronics, what if we can read a newspaper, and if you just click the button and if it starts to display and read it for us? So that loudspeaker has already been demonstrated by Chemnitz University back in Japan, in Germany. And this is all going to come now, because the things you all know about Internet of Things are getting connected. There is a cloud computing, and therefore the nanoelectronics, and if it is printed, the displays are there for us in a cheap manner. We can produce it, and everything is going to probably change in the next couple of years. And also the displays is a big market for nanomaterials and nanotechnology, where you can see the transparency. Wherever we want, whenever we want, we will be able to make the functional electronics as functional one. Also, this has a heavy applications in the military applications, because all these astronauts or military people would like to carry a lightweight materials rather than the bulky ones. Even the silicon-based electronics is very bulky, so they will need a lightweight. The lightweight is of primordial importance for them, and it has to be flexible and bendable, because the conformability is the key, right? So conformable means wherever we want, however we want, we should be able to produce the electronics. But that is not possible in traditional electronics or conventional electronics, because the silicon is a very rigid material, right? So it will not be able to bend it the way we want. So that leaves a ray of hope when we go up to the nanomaterials or nanotechnology. Other applications, as you can see, there is a plethora of possibilities, from the flexible displays to the way we interact with the using our ATM machines, or like the cards, and all these things can be bendable and flexible over the period of time. So those are the reasons why the curiosity of the nanomaterials and nanotechnology has actually emerged in me, and I started to pursue my research in this domain. Okay. So some of the other, technically speaking, those are like the material is printed or deposited on the flexible and stretchable substrates, and it is still functional. And the operating the temperature at which the function it can be functioned is very low. Low processing temperature is sufficient for that. That is the beauty of it. In silicon, the processing temperature used to be around 800 to 900, sometimes above 1000 degrees Celsius. We had to do the processing temperatures. So, but here everything becomes functional before 300 or 200 degrees Celsius, which is very easily controllable. Therefore, it becomes quite essential. Also, with this, the electronics becomes highly flexible, and also um, the solar cell, the applicability in terms of solar cell, because of these nanomaterials and nanotechnology itself, the solar cells will become very flexible. The biggest problem in the solar cell industry is that the solar cells are being kept on the rooftop and they are very rigid and bulky. So what if we were able to paint the home with a solar cell? That would have been one solution. Or like put the solar cell solar cell on top of the home, and if it is raining, bring it back and keep it in your home, and again when the rain stops, whenever the sun comes, go and spread it out. That kind of solar energy harvesting would have been the best ideal solution for that. The ultimatum is that something should be flexible, and it has to be non-rigid completely and conformable. So that is possible with nanotechnology, all of you. That is the reason why all of us should follow it up, isn't it? So if you see the OLEDs, if you see the curved OLED Samsung mobile phones, which is the new version of the Samsung phone, that is also a curved OLED. The curved OLED is also coming because it's an organic light emitting diode. The OLED is nothing but organic light emitting diode, right? So organic light emitting diodes are being, because of the nanoparticles which have been present there, they have been able to bend up. And the back panel to that OLED, which is switching it, is transistor, right? So all this will become very important one by one. We will go up and see to that. So further to that, after that, what is a more important thing is the nanorobots. The nanorobots are such a important aspect because all this cancer and all these viruses are not, we are not able to fight with coronavirus. It is just because it is at the nanoscale. Coronavirus and Ebola viruses are at the nanoscale. We will just see to comprehend and the scale and understand why actually we were not able to fight them and counter them like any other normal bacteria. Okay, so the nanorobots inside the body, we can be able to make it so small or miniaturized and able to defeat them. So that is the possibility, and let us see how the physics and the electronics works for that in order for this to happen, right?
Hello, sir.
So initially,
Let me interrupt you. Hello,
yeah,
Basu sir.
tell me.
Sir, participants are requesting you to go a little bit slow. So they
Okay.
feel, yeah. Thank you.
Sure. Oh, sorry. I mean, I was in my natural flow because I'm very sorry. So let us go it slowly because this was just an introduction. Now I will go and start informing you methodologically. Okay. So just to give a brief about myself in more detail, because I am from the same places where you all are, because I was in Belgaum. I am from a Belgaum district itself. I've done my schooling in Ankalgi. Then I joined RLS College and did my PU there. And then I joined the Vishweshwara Technical University, and particularly the MVJC College in Bangalore. And I have done my electronics and communication engineering. Post my bachelor's, I joined this Zhongjing Telecommunication Equipments is the name of the company. It is a Chinese company. There I used to work as a trainee telecom engineer, and I was placed in Malaysia for a couple of months there. And after working there, I was very curious, like all of you. I wanted to go to one of the elite institutions if possible. And I was looking up for the opportunities. Then the option came. The option came as the Manipal Technologies Limited selected me as its R&D executive. And they placed me in this National Center for Flexible Electronics in IIT Kanpur as a research engineer. And from there, my journey of being in the research world started. And then on, what happened is I because of staying in the campus, I was very motivated to study there, and I got selected for MTech in IIT Kanpur, which was one of the coveted institute at that point of time. And I did it in industrial and management engineering. My particular topic was understanding this technology and applying them in Internet of Things, understanding how the market works, how the technology works, being in conjunction with the entrepreneurial aspects of this technology as well. Okay. And then based on that, I got a under scholarship from King Abdullah University of Science and Technology, wherein I joined as a research engineer. And then I learned some of the things from there. And then I joined Queensland University of Technology in Brisbane now. Also, I have been to Japan, as said now. So we'll see what has happened is the main important thing is the exposure which we get once we are going into keep on going to the good institutes. That has helped me to broaden my knowledge. So I will like to be thankful to the Indian Institute of Technology, Kanpur. Here is where all these equipments which we use for making this nanomaterials and nanotechnology feasible. This is a sample center for display technologies, and these are the kind of machines which we will be which we will be using, and to get the results which we are going to discuss upon now. Okay. And then the King Abdullah University of Science and Technology, where I studied, it is one of the world's fifth richest universities. So it is a place where a lot of cutting edge research is taking place. These are some of the clean rooms for some of those who have not seen those photos. This is where all the semiconductor chips have been manufactured. This is the kind of yellow rooms, because the light should not penetrate and harm the device. They maintain the low intensity yellow rooms over there, right? So this was one of the laboratories which I used to work and synthesize my materials, or make the devices, something like all their technical work. So this was a very good learning experience for me. Then in Japan, this was the Japan. I worked with one of the very famous Professor Suzuki Tokito. They were the one people who were the pioneers of designing the OLEDs for the first time, and they have been designing all these flexible and printable electronics to a greater level. And then I had joined that Japanese group based on my PhD scholarship from Queensland University of Technology. This is the place where I stay in now. And my university was honored by the visit of our adorable Prime Minister Shri Narendra Modi as well. These are some of the technology. This was just to bring you to the perspective as to what I have done in the past, so that you will be able to comprehend the technical part of it. Now, let us go to the technical aspects. So let us start with nanomaterials. So what is nanomaterials is understanding is very important before we go to the technological part of it, right? So what do we call as nanomaterial and what we don't call as nanomaterial, and how to understand what is nano. The scaling is very important in this one. And then based on that nanomaterials, how this nanotechnology is developed and designed. That becomes, both are the two important separate topics actually. Many of the researchers are working on nanomaterials separately and nanotechnology separately. Those are two different dimensions altogether. But in this lecture, we will try to combine them and see how actually together they are functioning. So in this one, if you see the terminology, if we see, and nanotechnology, first is the nanostructured materials. How are those nanostructured materials, and what are the functions of it, and what are the tools and techniques used in the nanotechnology? That becomes very important. And also the most important thing is, what are the different type of nano devices which are important. So principally the nanostructured materials, if we see, those can be nanoparticles, those can be nanocomposites, or supramolecular assemblies which have been formed. We will not go into the chemistry part of it as to how they are formed. Those are formed by breaking the big molecules into smaller ones. So there is a separate possibility. If you just go in YouTube, you'll be able to find how this nanostructured particles are formed in the chemistry wise. Those are, for example, the metals like gold, we can break it into nanoparticles by there are standard procedures and protocols now, so wherein we can synthesize the nanoparticles from the core bulk material, right? Even for the silver or any other from the bulk material, the nanoparticles have been designed. Even the nanoparticles are designed from human hair. When we cut it, then at the nanoscale, when we go on, when we go to the nanoscale, the nanomaterials out of the hair are also formed now. So there is a lot of ways in which the nanostructured materials have been formed. The main other thing is that how these are fabricated, how these are instrumented, what techniques and simulation softwares. Also, the main important thing is there are something like micro electrical mechanical systems, which are called as MEMS, and there are biomems. The nano devices have applications in all of them. from sensors to detectors to systems on chips. So for those of you who don't know systems on chip, chip means it is just an IC, right? If a chip consists of battery, IC, Bluetooth, everything in it, then it is called a system on chip. So the nano devices nowadays, even now in the company, I am working on systems on chips. So the systems on chips are like the whole system on a chip itself is there. So you don't have to connect any additional thing other than the battery to it. So that is called as systems on chip. The research is going on very vibrantly in order to make those of nanoscale. For example, for all of you to comprehend, the latest Intel transistor or the chip, whatever you see, Intel inside Pentium 4, some of you might have heard. The other Intel ones are made of 10 nanometer transistors. The channel length of the transistor is just 10 nanometers. So that's why the speed of the mobile phone, whenever you start to work, it is so fast that these days, right? That is because the transistors are at the transistor channel length is at nanoscale. Okay, so that was just to bring into perspective. Now if you see the macro and macro, nano, and macro, micro, and nano scale, so this is the difference. So when you see a bulb, you can consider it as a macro, and something which is a gear or something where you can see it still, or sometimes you can see it by a microscope. So generally we use a microscope for a micro range, right? So but the macroscope, we don't need any scope, we can see it from the naked eye. But the microscope, at the microscope, we will start to need the this one microscope. At the nanoscope, there is nothing like something called as nanoscope. So there should be some other tool in which you can see it is so small that we will not be able to see it. So basically what we will do is we will try to see how people see them when it is so small. There was a microscope, but how to see this at such a small scale? If it is, then what small scale I am speaking now? If you see this one, the generally if we see the ant is around 0 millimeters, right? Or you can say that in the human hair is hundreds of nanometers. It is still not in a nanoscale. It is, I am talking the size smaller than one human hair, 1/10 of the human hair or 100th of the human hair. I am speaking of that scale. It is so small. So at that small scale, we should be able to fabricate and synthesize the materials. The materials will be of that scale. The devices have to be of those made from those scale materials. All these things. So the divisibility is very high, and we have to see it. So now just to further make you understand, so if you see the baseball bat, it is around 1 meters. The fingertip is 1 centimeter. And then the needle or the needle eye is just 1 millimeter, right? And the human hair is around 100 microns. So human hair don't call it as nano device because it is in micrometers. Micrometer is 10 to the power of -6, right? When I say about nanometer, I am talking about 10 to the power of -9. It means 1 divided by 1 into 9 zeros, right? So it is so small. So now if you see the blood cells are generally 10 micrometers, right? So blood cell. And if you see bacteria is 1 micrometer. In according to me, bacteria are very bigger because in microscope you can easily see and comprehend them, right? Bacteria are 1 micrometer generally in scale. But if you see the virus is 100 nanometer. Actually, from 100 nanometer to 1 nanometer, we call as nanotechnology. So anything above 100 nanometer, we don't typically call it as a nanotechnology. So anything below 100 nanometer and up to 1 nanometer, we call it as nanotechnology. So virus is at 100 nanometer scale. So the scale of virus is very, very small. So when it is very small, how to understand and interact with it and create a solution for it becomes very, very difficult. So that is one of the reasons, because of its small size, the vaccines are not able to produce for any kind of viruses. It might be AIDS, which we call it as acquired immunodeficiency syndrome. It's a virus. And even the corona is a virus. So, and Ebola was a virus. So if you see, most of the viruses don't have a proper solution because understanding at the nanoscale has not been so evolved. There has to be a lot of research to be done in that. There is a lot of scope and possibilities. And then also the half of the DNA. So like the DNA research is also a very famous research. All of you know that the moment you go to the DNA scale, the DNA is 1 nanometer scale. So whatever I am talking now is at the scale of DNA and the virus. So it is so small, okay? And then now, as we know that from water molecule, which is very small, to this virus, which is around 100 nanometers. So in this one, but the materials are of these sizes or scale. So the graphene is one such material, other such materials are here, and the other materials, other things like human hair and ant are very, very big in comparison to what our materials are. So some of the very famous nanomaterials are fullerenes, carbon nanotubes, graphene. You know how graphene is formed? The graphite is taken. From that graphite, a thin sheet is extrapolated. So then the graphite is formed. So graphene, that is a 2D material, they call it. It doesn't have three-dimensional. It is so small that only XY plane can be formed. The Z plane will not be able to be formed from that. So therefore, that is becomes a 2D material, right? So now if you see the nanomaterials versus the bulk materials, what the difference was that the nanomaterials, in case of nanomaterials, the size was 1 to 100 nanometers. In the case of bulk materials, all the size was very, very large, right? So therefore, the visualization was possible in the case of bulk material, but in the case of nanomaterial, the visualization will be very, very difficult. And with the naked eye, we will not be able to see anything there. So it becomes very difficult to understand. So there has to be a separate apparatus, separate system, separate methodology to be designed and developed in order to understand nanomaterials and nanotechnology, because of the sheer scale of the things which are very, very small, isn't it? So some of the examples are there. The nanoparticles based graphene is one such example. If you take the bulk material, all these periodic table elements generally at their scale are when they are in the material form, those are bulk materials, right? So from those bulk materials, these nanomaterials are synthesized in the lab. So once they are synthesized, those are processed now. So we will be seeing how those are processed, what will happen, right? So now, before we see that, we have to understand what the moment we make the material from the bulk material, if the moment we make it smaller, what actually happens? What actually happens from the bulk material if we bring them to the nanoscale? Then what will happen is the catalytic efficiency will increase drastically, because from one atom we have been able to break it, like we have been able to break the molecules or something and make them larger, right? So what will happen is for a particular volume, the surface will increase. Also the electrical conductivity will increase, and in the metals the resistance will decrease. So what does resistance decrease in electric metals mean? The moment the resistance in the metals decrease, they tend to become a slight semiconductors, right? The metals have to be superconductors, I mean conductive. So if I am able to tune the resistance in the metal, it means I am able to make the metal back into something which is semiconductor kind of stuff, isn't it? So the increased electrical resistance will take place the moment we bring them into the nanoscale. Also, the most important thing is the magnetic phenomenon. The moment you break the bulk material into nanoscale, what happens is the magnetic coercivity increases. It means the probability that which the resonance of the electromagnetic forces will start to act on that particular from that particular material will be very, very high. So what happens is the properties and the requirements of the whole physics and dynamics keeps on changing the moment we go to the nanoscale. So along, not only with that, each of the other possible physical properties like mechanical properties, if you see, the hardness and toughness which was there in the material, in the bulk material, will dilute now, and it will become very easy for anyone to tuke around to make it conformable, right? Also the optical phenomenons, for example, what happens with optical phenomenon is the absorption spectra, which whatever is there in the absorption spectra, whatever was there in the bulk material, now it gets to be tuned. So the moment you start to tune your optical spectrum, what happens is we can operate them devices at the place where we want and the way we want. That's how the solar cells have been getting formed. So because at the required optimal absorption spectra, they can resonate back. Therefore, these things will happen. And then if you see, the most important thing for robotics, when the nanotechnology, nanomaterial starts to become used as a robots, is because of the spherical and the biological properties. The moment you increase the decrease the from the bulk material, if you come towards the nanoscale, what happens is the selectivity increases. So the material will start to react and sense for even a minute changes at the nanoscale. So the even a small part of a material, bulk material, will be able to selectively react back to something. So therefore, whenever the drug transportation happens or the drug release happens, there will be a net change immediately after the goes. So, but if we had to, if the bulk material had to react, we should have needed a more space or complexity, right? So therefore, the spherical behavior of the nanoparticles is very important. Also, the biological aspects of that will be very important, which we will be seeing ahead. Okay, so some of the applications therefore are huge because of those advantages. The applications starts from medicines. So from the cancer diagnostic, we will see how the cancer diagnostics is done with the medicine in the medicine field, and the nano biosensors. The food and cosmetic industry is heavily using it. All those wrinkles which are there in the face because of the nanomaterial based printed heaters or something, they can go back, they can go now. So all the cosmetic industry is heavily crazy on this food and cosmetic part of it. So we can see that the nano size powder, increased supplement intake, so those kind of stuffs are coming up. And on the environment and environmental scale, the moment you start using this nanotubes, right, or they're called as carbon nanotubes or other nanotubes are available nowadays. So these nanotubes increase the efficiency, because when you transfer the electrons in that tube compared to the surface, what happens is that in the tube, it will be the net resistance will be very low compared to the surface, right? So therefore, the efficiency and speed with which it will be transferred will be very high, and it will not be having generally the impact on environmental impacts on that. So these are the very important applications. Other applications, of course, are like we have already discussed, saying that it can be make it lighter, smoother, and conducive for various other properties, right? So because of that, what happened is in the 1959, there was a researcher called as Richard Feynman. He is very famous person here. He said, he had already said in 1959 itself that there is a plenty of room at the bottom. By that he says, the moment you go smaller and smaller into the materials, what happens here is the amount of understanding you have to do is very, very huge. So one thing is going into space and seeing what happens in space, but one thing is going back into the smaller scale of materials. Then there is a lot of opportunities and understanding which it has to be done over the world. He has said it. Accordingly, what happened is in 1974, they coined the word nanotechnology. Okay. And then the scanning tunneling microscope, they call it as, that's what I told, microscopes are no more useful in the nanoscale. Nanoscale will need a separate microscope, which will be like a, which will be able to make the feel of those nanoparticles and nano size. In 1981, the scanning tunneling microscope was invented, and that actually exploded the innovation to go to quadrant. Okay, and in 1989, the IBM already what it did is it extrapolated the ions, and then it created its logo. IBM. These are the ions which have been created from the bulk material, right? So the IBM name has come. What is IBM now? IBM is International Business Machines. So the full form of IBM is International Business Machines, right? That logo has been generated by removing the individual genome items. Okay, and then in the 2000, the committees have been formed, and just from 2000 to 2016, if you see, the diffusion of this technology is tremendous. Okay, there have already been 2 Nobel Prizes in the physics. The Nobel Prize has been given because they were able to isolate the materials. As I said, they were made 2D, and 2-dimensional materials were formed, and they were not having the Z plane, and therefore the resistance was very low. So the graphene materials are very, very famous nowadays because of their electrical conductivity and the increased conformability. Okay, and in the 2016, what happens is the nano car was invented, nano car prototyping was done, and they also got the Nobel Prize. So then a couple of Nobel Prizes here in the field of this nanotechnology itself. And so therefore it becomes very interesting to see how actually it functions and works. So some of the other applications here are like, as we have already discussed, that the biosensors and sweat biosensors, contactless biosensors, all these things can be created. But the problem again now is If it is only small, it is not enough. You know, why it is not enough? Like if I put a small one into my mouth, what happens is still it is a dangerous thing to put that kind of stuff into your mouth and then keep on monitoring it, right? So it has to be also biocompatible, and also very, very flexible. Otherwise, so that, and also it should be low cost, so that you can remove it anytime and throw and then again reuse. If you keep buying this kind of expensive chips in for any wireless transformations into your teeth or anywhere, which will become very expensive and it will become very difficult. These are required when there is a mouth cancer, the tooth cancer, or some other things where the diagnosis has to be continuous and more frequent. So then this kind of applications will be there. So there the flexibility will be playing a key role, and there the materials which are so small, which are very flexible, very controllable, play a key role. Okay, so therefore the transparency, flexibility, and although the speed of operation is low, these becomes important, and low cost are the key, because the low cost means we can develop them even in a developing countries, right? So we don't have to invest a lot of infrastructure in order to design and develop them. We can easily develop them anywhere we want to. Therefore also other applications is we can detect because they are low cost and flexible, anybody and anywhere can start detecting the viruses. Like for example, all the coronavirus and Ebola viruses were defected, where somewhere the nanotechnology has contributed on them, because the virus is at nanoscale, as we have seen during the scaling process. We have seen, right? Virus is at nanoscale. So the material, which is a graphene or something, it is also at the nanoscale. So the nano interacts. But what used to happen before nanotechnology is that the virus was nanoscale, but the materials were bulk. So the nano used to directly penetrate through them. So now they are of the same size. So the enemies are same. Like it can't just penetrate through the porous system without getting detected. It will get detected at the nanoscale. So therefore the Ebola virus got detected. That's how then coronavirus also got detected basically. So the lot of research going on this kind of flexible based nanotechnologies, and particularly this transistor. If the transistor changes, as you all know, everything changes. So even in the silicon industry, it was basically the transistor which actually changed revolutionized the whole world. So for all of physics enthusiasts, we have to understand the concepts of transistors and the circuits, and which can be used for this kind of detecting, sensing, and many other applications. Okay. So on the basis of that, also it becomes important that along with studying the transistors, the main important thing is that if you see here, this is the antenna. That is also a nanoparticle ink which has been printed here. The nano ink this is. So this is an antenna. Generally, if you see an antenna, if you see in your home or behind your TV, or before you used to use this dish, it used to be a big antenna, right? Now the antenna has been printed on a piece of paper. It is just a piece of paper or a piece of cloth. On that, I will use my inkjet printer or any printer in my home, and we can print that antenna, and it is like coil. So it is basically an inductor. So an inductor, whenever you bring another inductor, so the mutual inductance takes place, the net transfer of electromagnetic signals takes place, and therefore the signal can be transferred. We all know there's a basic physics, right? So that happens, and we are able to bake that kind of inductors on a piece of a sheet or a piece of a paper. That is a huge revolution, right? So similarly, the printed transistors are being done, and the solar cells, all these stuffs are coming up, and the gold nanoparticles and the silver nanoparticles and gold nanoparticles play a very, very important role based on the application, right? And therefore, because of that, because those are being printed on that, we can print those nanoparticles on the piece of a glass or any other substrate, and it will become conductive. Therefore, now other application is that now we shall make it printed on a variable substrate and stretch and strain it, but still that electronic should be able to work. So the moment the electronic starts to work on these also, each and every material or the cloth we wear, it will become active. It will become active, and it will have some signature in that, electronic signature in that. So this becomes this is where the nanoparticles and nanotechnology is going to contribute immensely and effectively. But particularly in this one, as transistor is the main base of all of these, we can see here why transistor becomes very important. If you see this one, this is one of my research group back in Saudi Arabia. I had shown you the photo before, where I had studied, done my research basically. So there, that group has designed um, antenna. This is an antenna. This is a gold nanoparticle printed antenna. Okay, this is a gold-based nanoparticle. They have printed it, and this flexible antenna can do a 360-degree communication. So all the way it can detect, and that has been placed on the on top of the shark there, on the fish or shark or whatever tortoise, on all of that. This is done in the Red Sea. It is just beside, there is a coral reef there beside Saudi Arabia. So on that one, they have placed this kind of antennas. So these antennas, one part is antenna, but there is a chip. You see, this chip, the antenna is doing all the communication. The wireless network access is being done with the antennas, but the chip is basically what has the transistor in it, right? So transistor, what if that chip also could have been printed along with that antenna? This would have been a huge stuff, because we don't have to do a topmost encapsulation to protect that chip. Now a lot of money has been spent in order to protect that chip. Antenna is okay, antenna, because it is made of nanoparticles and it don't interact with water, and they have encapsulated it and everything is fine. But encapsulating the chip properly into the water surface is becoming a big deal. So the transistor printing has become very essential and necessary for this to become reach its full potential. Okay, so on the basis of that, we shall see that transistor. What is that transistor? Thin film transistor, because all of us are, many of us are physicists and electronics engineers. So what basically happens is the thin film transistors for sensors and circuits based on nanomaterials becomes a very important thing to understand. Okay, how actually it performs. You all know, all of you have learned MOSFETs and N-type, P-type transistors. So the same thing is going to happen here with some minute changes, which we will discuss. Okay, so why that OFETs or the field effect transistors and the flexible printed transistors? Because this flexible printed transistors are used everywhere. They are used from the electronic skin. In the Japan group which I was working, we were trying to make the electronic skin for the robots. So the robot should be able to distinguish between a man's touch and a girl's touch, right? So it should be able to feel. They should be able to feel the difference between the sensitivity. So that was the level of which the Japanese group is working, and they are trying to make some highly sensitive. So the electronic skins have been generated, and the sensor is behind that is a transistor, and the wristwatch behind this, the main part, and because this is a OLED, and to the back panel of the OLED, there's something has to control those OLED pixels, right, one by one. That is done by transistor. If you see the flexible display, also behind this flexible display, there is a transistor which is switching all the LEDs, which are all the displays here. And the flexible display is only possible because before, why the flexible display was not there? Has anyone thought of it? Why is it possible? Why were the devices were not flexible like this? Why were we not able to bend our phone? It was because it had a silicon, and the silicon was non-conformable. It has to be rigid. So the material has changed. The material has gone to the nanoscale, and at the nanoscale we are tweaking from the nanoscale itself. The material has been formed now over the period of time. A lot of researchers have contributed, and they have made such that the material can be printed on any surface. So that is the reason why these bendable displays are coming into picture, and so there is a lot of opportunities in that. So in all of these, as you all know, some of you who have been dealing with electronics know that ring oscillators and the transistors and then the inverters and then the circuitry becomes very important, because when we keep on building the transistor based circuits, the high complex electronics starts to come into picture. And then if you see in the robotics, the robot's sensor, the robot's eye is basically a transistor, because the transistor, on the basis of the transistor itself, the robot will be able to detect what is going on, how much is the threshold voltage shift, what actually happens, and everything comes from the basis of the knowledge of transistor itself. So therefore we will be seeing that. Now why transistor has to be printed? Because when we see that the transistors are very expensive in CMOS technology, and the supply voltage is low, but in the case of nanoparticle based transistors, the supply voltage is still around 1 volt. Okay, but still it's sometimes it might range in between 1 to 40 volts. So that is one of the drawbacks. But other than that, the other things which will be there is the low processing temperature. Like only we need 100 degrees Celsius and room temperature to process them, and there is no need of high level lithography. Lithography is a very, very complex and complicated subject, wherein you have to have very high-end materials in order to allow the light to flow through them and something. So here it is just, and it is a subtractive process, you know. Yeah, the CMOS and all the chips, whatever we are seeing, is a very subtractive process. You have to, first of all, put all the material there, and then you have to remove that material from that surface. So the material is waste, right? But the inkjet printing, or like anything which is related to nanoparticles, as it is additive, wherever we want, we can place it there. So that becomes a very important process technology, because of which all these advancements will have will save a lot of cost. And for the countries like us, we should be very pioneering in this kind of field, so that the we can produce anything at our local markets itself, without depending on anyone else. So this becomes very primordial for all of us to understand. And on the basis of that, we will first see what actually is this transistor, which is playing a key and pivotal role in all of those above discussed applications, right? So there is a lot of theory to that. So we will see basic stuffs. Like you all know that in any device, this is a gate electrode transistor. Whoever knows the transistor basically is that there will be a gate electrode, gate dielectrics. There will be one kind of semiconductor, which might be organic, it might be inorganic, it might be even the silicon, and then there will be a source and drain. Between the source and drain, the electrons and holes transfer, and this happens. So there are some of the approximations which have been done now. These are like something is called as gradual channel approximation. See, behind all of these concepts and technology, it is all physics. Okay, if we don't know physics, we don't know anything. And the physics at the nanoscale will change drastically compared to whatever physics we know. So physics, what we know will aid here, but the physics here will be different. So that is the beauty of it. Now, all the equations which we know for metal oxide semiconductor field effect transistors, which are called as MOSFETs, are changing now. If you see the moment we come to the nanoscale, because this material is in nanoscale, all those equations will keep changing, and the approximations we have to do is completely different, right? So something is going on the screen. I don't know. Sorry for that. Okay. Yeah. So yeah, okay. The gradual channel approximation, if you see with this one, what they say is basically that whatever the charge is there in between, whatever the charge I apply at the gate is sufficient enough, and there is no resistance in between the source and drain. That's what it is saying. For those of you who want to explore, please explore that. There is a very important concept there, how the charge transfer takes place. And then if you see the equations there, we know
Sorry
the
to
typical
interrupt you, sir.
equation.
Just a minute. Hello.
Yeah, yeah.
Yeah, if you can erase the pencil marks on the screen. I think if participants have written, please erase. I request all the participants to erase the pencil marks on the screen if by mistake they have done. Go to annotation, clear all your drawings.
Yeah.
I request all the participants to erase by mistake if they have done.
Dr. Vinay, what I can do is I can stop the share, and I can again
Yeah,
reshare it.
exactly. Yeah,
Okay.
it's better.
1 second, please.
Yeah, sir, you can reshare. Yeah.
Yeah. Is it visible now?
Yeah. Thank you.
Okay, thank you. So so the equations, this is just I am showing because it is very difficult, I understand, to comprehend it within a one moment and in this fast phase. But just try to understand that the physics is changing here. That's what I want to basically show you all, is that the moment we go to that nanoscale material, the physics completely changes, and the equations, we have to rewrite all those physical equations. So a lot of scope for a physicists and all those chemists and and technology enthusiasts, like how actually these things are working at that nanoscale. What is the underlying physics behind those phenomena? We have to see. So the linear region equations of the OFET are going to change. The saturation region of the OFET is going to change. And if we see that, on the basis of that, we all know that how that OFET works, right? If field effect transistors work, they will be having an output characteristics. They will be having an output characteristics where they will be saturating at this region, and there will be a linear characteristics. There will be a transfer. And what does mobility mean? We say that, oh, my mobile phone is not working fast. Mobile phone is very slow. It is basically this mobility of the electrons or holes in that layer which are transferring. If the electrons and holes are transferring very fast, then the device or the mobile phone or whatever tool we are using, it will be very fast and very fast operating, right? So all this speed we are talking about, the mobile phone is very fast or slow, is based on this transistor speed. The mobility is very high, then it is very good. If the mobility is very low, it is very low. Or and how fast it is able to sense. If the transistor is able to sense very fast, like you can see here, the transistor here is getting on at 10 minus 10 volts. It is very slow comparatively. So now some of the work at 0 volt itself, at even 0.1 volt, they are able to detect. So that kind of detectivity is essential. The speed and detectability is very essential, right? So therefore the equations of all these change. This is how we calculate the mobility and find out that this particular surface is having, or this particular material has a high mobility, and this is a good material and this is a bad material or normal material, something like that. Also, a lot of physics has to be studied in terms of surface trap phenomenon. The moment we put this material on some surface, there's some of the charges, that electrons and holes, get trapped now. This kind of phenomenon was not there generally in conventional electronics, because the conventional electronics was a bulk material, and the bands used to get formed. The band used to be covalent, valence band, right? But in this nanoparticle based, generally there will be a HOMO and LUMO. They will be operating in the HOMO and LUMO levels. What is that? For highest occupied molecular orbital and lowest unoccupied molecular orbital. This operates. The proper banding is not formed in case of these nanoparticle based materials generally. So therefore, the surface traps and all these phenomenon starts to keep on increasing the moment we go ahead the nanoscale and nanoscale based devices. So the completely new device physics has to be invented, and people have done sufficient contributions already. So first of all, it is important to understand it, and then comprehend, and then make some changes. So on the basis of that, those devices can be formed, as you know. I will just skip it, like saying that the different way, the architecture of those devices. Now, if you see, this becomes very important in that device. From the source, if it is a P type, from the source we can transfer the holes. If it is an N type, if it is an ambipolar, you know what is this ambipolar? Ambipolar is actually a OLED. Electron is also coming and hole is also coming on that surface, and when the electrons and holes on the same surface are coming, the light is coming, right? So on this particular surface, I will show you it's in the next slide. So what actually happens in OLED, I will show you. So there's one particular surface, in that channel itself, we are able to impose electrons, and from one side and the holes from other side. So therefore the light is getting evolved. So that is where the ambipolar behavior will come, and the N type of behavior is one, only the electrons will get formed there. So then we call it as N type. So this N type and P type are the basics for circuits, right? When we put one N type and one P type, inverter is formed. When those couple of inverters are formed, then we form a ring oscillator, and that is what is there in your blue chip or a circuit. A couple of these transistors, billions of transistors are there. So these are the basics of which word works. So let us see, like these are the biasing stuffs. Like the moment we start biasing, how they operate. Let us leave those parts. The basic thing is here. The gate is here. The moment I apply the gate, the voltage, what will happen is the channel gets formed there in between the source and drain, because this is a capacitor. If you see, this is a metal, gate is a metal, this is a dielectric, and this is another semiconductor. So whenever there is a capacitor, there has to be a field, right? So the capacitor will always generate a field. So whenever I applied the gate, the field got formed. And whenever I applied the potential difference between the source and the drain, the charges get formed there, right? The source and drain, this holes and electrons. Now, because of the fact that both source and drains are being able to form, if from one side, if I send holes, from one side, if I send electrons, the OLED will form. Okay. This is what is the basics of how the transistor works. And then based on that HOMO LUMO, because the banding is not formed, we have to tune and reduce the resistance from this point to this point and this point to this point, and the electrons will flow fast, and we can catch from one side to another side. So therefore the controlled diffusion of charge carriers takes place, right? In the case of P type, where only the holes will be there, okay, and in the case of N type, only the electrons will get formed in the channel. So that is the basic difference between the N type and P type. So proportionately, the biasing and all these stuffs has to be changed. Now I will show you some of the materials like donor acceptor type materials. Here, what happens here is, what happens with nanomaterials is, it will become very easy for us to tune the band gap of the semiconductors. So what happens is, the moment we go to the nanoscale, in the case of silicon, the tuning of that material was very difficult. If the covalent bond is there and if the valence bond is there, that bonds used to be fixed permanently. Now, in the case of this one, because we are going at that so small scale, we are able to tune that covalent bond and valence band the way we want. It is means that we are able to completely control at the atomic level itself, right? Because we are able to tune the HOMO and LUMO, or that the covalence band and condense bond generically, we are able to tune that. So therefore, we are able to make anything as we want. So that is the beauty of this. So these are some of the examples. That's all. Some of the other materials which can be formed based on these this kind of tuning is been described here. The mobilities are keep on increasing, and now already the mobility of around 12 centimeter square per volt per second. The moment we put 1 volt per second, 12 centimeter square is the shift of the holes or the electrons which is taking place. So that is the beauty of that. Now how we do it, that I know that was quite intriguing part, which it will become very difficult for you to understand when you are not the physicist. But here you can see how actually we will be able to do it. We take a normal silicon wafer, for example, or any flexible substrate. We just put this solution on top of this, and then we deposit the materials, and then spin coat. If required, we can inkjet print it. Any other deposition can be done. Even we can put it on, we can take it on a syringe and put that material on top of my substrate and deposit those top metals, observe if everything is fine, you are ready. Your transistor, your sensor is ready. We can do it at home, I mean, over the period of time, if everything is well done. So therefore, and once it is done, you have to just do a simple X-ray pattern diffraction analysis. You could to find out whether that material is conductive enough or whether it is crystalline or amorphous. We can find out from this XRD, you know, right? So the XRD, whenever we do the thin film XRD or a bulk material XRD, we can find it out. And therefore, we can see the full width half maximum, saying that where is this intensity? If the intensity is very high or very low, based on that, we can find how crystalline the material is. So even after playing at the nanoscale and even after tuning the bands, we were able to find the crystalline material, somewhat crystalline material. That's a huge achievement. And that achievements actually lead to technological innovations. Having said that, now how are we seeing that? Because the nanoscale, we don't have a nanoscope. So we said that there is a scanning tunneling microscope. One such thing is scanning tunneling microscope. Other one is the atomic force microscope. This is an example of atomic force microscope. I was able to go to that atomic force microscope, and based on the roughness, for example, if you see, if I do some treatment, if I anneal it more, the roughness, the changes, and therefore we were able to tune it, right? So all that things happen. Now, what are the tools we use? These are some of the laser microscope images which we have to use and understand how actually what actually is happening on that surface. And these are some of the other other tools and techniques which we need at the lab scale in order to deposit those metals and stuffs. And these are the how the characterization takes place at the lab scale initially to measure the transistors and circuits and all this nanomaterial based technology. So sophisticated equipmentation is essential. So that's where we have to go to we have to aspire to go to the some of the institutes which have that kind of facility. Therefore, that's where we have to compete and get into those. So in order to access this kind of facilities at this scale over the period of time, I think so these will become generically available at every other universities as well. So now there are some of the research gaps of that transistor. We will just with that transistor. What happens in the transistor is the moment you the other thing, but the surface engineering has become very important. The moment you change the surface by putting some other material, what happens is, now if I put a water here, it is important for you to see the surface engineering is important. The moment I do some treatment on that particular layer, the water used to be at 82 degrees, right? So now the wettability of that water or any other polymer will change the moment we change the surface. So at the nanoparticle range and nanotechnology range, what happens is the surface, how the surface is behaving based whenever I put my material on top of it. Any other material, for example, if I put a Ebola virus on top of mine, so the surface phenomenon changes suddenly. So the surface, understanding the surface phenomenon has become very, very important to understand the dynamics of that. So this was one example for you to understand. And then once that is formed, we have to do the passivation, because the passivation is important because the device degradation and stuffs will take place. And so along after that, what happens is we can form a dual gate. When the dual gate is formed, the sensor is formed now. So this was basically the sensor which I was talking about. And if you see now, if I change this top electrode based on controlling the top electrode, for example, now if I put a Ebola virus here, instead of by removing this top electrode, if I put my Ebola virus, the shift in the voltage will take place like this, or it might go anywhere, right? The moment I change, because the whole device is coming up there. So the moment I put, if I put a coronavirus or any other virus or any other entity, this shift is going to take place. The moment this shift is going to take place, we can, over the period of time, we can electronically say that, okay, this virus, if this much extent is put, then this much change I should see in this. This is semiconductor, because that virus is also at nanoscale, and the organic semiconductor or any other semiconductor or nanomaterial will be at that nanoscale. So both will interact. The moment they interact, the shift is going to take place. So based on this shift, we will be able to find out, okay, that was that particular virus, or what particular antigen, or whatever it might be, the bio receptor, whatever it was. So on the basis of that, we were able to find, and we have developed, that was the work. And this is under work, where you can see that now, based on that transistor itself, the circuits have been built, right? There is a battery which is also printed here, and this is my Japanese team which has developed this. So this is the ionic based electrodes. The Bluetooth is there, and it is on the skin. It can detect your nerval tendency, as how it is changing. The moment it changes, the threshold voltage and the parameters of the transistor will change, and everything can be understood, right? So the transistor has becoming playing a vital role now, if you all observe it, right? So it becomes very important to study that. So so physics is there, a lot of chemistry, a lot of, so there is a, this is called as, therefore this branch is called as intradisciplinary. Okay, so now we will go towards the nano robotics. Okay, before nano robotics we go, I want to tell you that if you are only a physicist in this modern world, it is not enough. If you are just a chemist, it is not enough. If you are just an electronics engineer, it is no more enough. So it is not enough to be just one. You have to be dynamic. For example, I told you a lot of things about materials, about chemistry, about electronics. So the things are like, we have to be open, and there is a lot of mathematics as well. So if I don't understand mathematics, I will not be able to tell all these things, isn't it? So we have to be open-minded at our early stages of education. I think most of you are, so that all those disciplines have some value. Only we are not able to find it probably. So therefore it becomes very essential for us to become transdisciplinary. And what is transdisciplinary? Transdisciplinary is nothing but being active in all different possibilities of knowledge, okay, and trying to get something. For example, chemistry is important. Just if you say that, oh, I am a physicist or a chemist and I don't get a job, you are not one, probably one will not give in this modern and dynamic world, because the world is coming up with all this nano stuffs, and so many things are interacting with each other. You should be having the knowledge of other subjects as well. It becomes very important and crucial. So that's what that was just a part of advisory when I was going through. So the possibilities of advancements now those nano stuffs, whatever the transistors have been used in this nano robots, right? So nano robots have been prototyped now. Now why this nano robots becomes important is, if you see this nano robot, the nano robot is able to, because that transistor based nanorobot is at the scale of that virus itself, or if it is a cancer cell disease, it is able to go and put something which is opposite, which will kill that. Until now we were not able to do that. That is the main reason why cancer had not so cure. And the big ray of hope is the nanotechnology and the nano device. And when it is made in this particular form of nanobot or nanorobot, it can go and fit it. It can go and kill it. So there is a lot of tremendous amount of research which has been going on. And if you all see here, the tumor, what will happen is they will leave the tissues unharmed, living healthy tissues will be unharmed, and only where it is required, there it will go and pinch and put the whatever this molecule or solvent we want to put, it will go and fix it there, and it will kill that particular part which we don't want to do. That was the biggest problem of cancer, that cancer cell keep on repeating and reforming. So every time we have to go and hit it. And these nanorobots can be electromagnetically controlled from outside. The doctor need not always inject them. So once you send it, it will use the electromagnetic force which is there from one molecule to another molecule, and it will be there inside and outside also, because of its electromagnetic. I had told that whenever the nanoparticles come, the electromagnetic tendency will also increase in them. So this has also the electromagnetic tendency. So we can find out where that robot is, that nanobot we call a robot. that we can find out from the outside. So that kind of research is coming up very high, and even the DNA can be altered. The problem is that because now we will be at from the nanoscale, as we have seen before. The nano DNA is at the 1 nanometer scale. So now the moment we bring this, so there will be a high tendency that at the nanoscale the DNA variations can be done, but still it has a very controversial topic. One will not interact with the DNA, but there is a possibility at that scale, right? So what happened is the professor at NCTT said that the blood tumor supplies the blockage, and this kind of nanobots are able to go and kill that particular tissue which was very, very critically harming the whole body system, right? So therefore the possibilities are huge, and because the moment it comes to health, uh, the research will go very fast, because all want to survive and for long. So that is what is happening with nanotechnology and robotics now. So they want there is a lot of success. This one was successfully programmed. This is a programmable nanorobot, right? So the Arizona State University have been a couple of my friends have been working on those departments and the projects there. They have been very serious work, and they can program it as well. So they are being able to develop a prototypes and say that okay, it can be programmable now, because the chip is also there, and it is biodegradable chip inside that, which is made of a transistor. So what happens at the end of the day, you don't have to remove this robot out. It can just biodegradable. So in your body itself, you can just tell it to collapse, it will collapse it within there, and it will come out of your body system. So you don't have to do any lot of surgery or something like that. It will be very easy to deal with this. So a lot of stuff has been going on. There is other such detailed analysis for all of you who want to do something. Actually the biomedical stuff, the moment the value for physicists has increased a lot these days, because even the medicine and the biomedical, the moment the medicine finishes, it will be all physics and scientists who will be working, and they want to understand the physics and dynamics of how these things work. So for example, that cancer treatment, it's all waiting for the good physics to occur, because they have sufficient materials now and everything has been designed. But what will happen, like which particular, how is that electromagnetic wave which is going from year to year, how to control that electromagnetic phenomenons in between that, what is the principle, what is the theory, what is the logic that has to be done, and what kind of formulas are actually able to tweak them. So is the formula what we have written is relevant, or some substantial change has to be done? That kind of debates keep on going on, and therefore there is a lot of scope. And we can see that then the tumor, if we observe clearly, it is available in the Google. If you can just type this Arizona State University nanobots, you will find out that, and you can see that they are able to create some of the DNA tumor targeting locations into the bot, and they will go and place them into the required desired DNA level places, so that if the DNA is altered, or if the virus's DNA is altered, everything will alter. So it will become very easy to kill the coronavirus. If the sufficient research would have been done in nanorobots, it would have been not a big brainer to overcome that virus. So that was but still now the value for this kind of research is coming up because of contagions. Also there are a lot of things, not only at the cancer level, even at the heart blockages. The blockages can be removed by these bots. They can go and precisely remove and target, because it's at a nanoscale. If they do something wrong, we can just program it and say destroy. They can also go into they can also diffuse themselves and degrade into the body itself, and all the signaling and stuffs takes place. And even in the diabetic patients, the glucose monitoring becomes very important, and the moment that content has to be reduced now when they reach the critical stage. So people have shown that, they are particular. How it works is, they make a nanobot has become a very common thing, and they put their receptors or antigens or whatever it is, and they send it into the body, and they try to see whether it reacts to that one at the lab scale. All this work is still now at the lab scale, at the nanorobot scale, nanorobots. So there are many emerging stuffs, I think, so which will be coming in next couple of years. We have to stay tuned and see those things, because nanotechnology is going to play a huge role in this robotics environment. These were some of the references here, I think. So I crossed my time, and so I'm thankful to all of you. Please ask me any of the questions if you have.
Yeah, thank you, sir. The session is now open to questions. Participants, please raise your hand.
Yeah, feel free to ask any of your questions or doubts.
If there are any questions, participants can type it in the chat box. They can raise their hand. There is a question in chat box.
Yeah.
So, will the
Yes, sir.
AI and robotic world rule over the humans?
Yeah, that is a very good question. Yeah, the artificial intelligence is the core of all of these things. So robot is robot robot in itself is not of very value if the intelligence is not there, right? Only the intelligent robot is a big problem. So AI is a very important thing. So basically, when the when I said something about transdisciplinarity, right? So what does the core of the transdisciplinary research is ethics. So somehow we have to train the ethical procedures and protocols like the humans we have into these robots. So there is a completely different branch of study which is like doing training ethics to artificial AI. So Harvard and Cambridge all are working on those aspects of see, the robot is essential, artificial is essential, that is, there is no doubt. The moment they become more smart and smart, they might have an adverse impact on human beings. This is a very good question, and what will happen is they have to be trained accordingly. So that has been done now. So there has been a separate branches in the transdisciplinary subjects wherein how to emotionally train them from the day one and make sure they are very conducive. So yeah. So
Thank you,
anyway,
sir. Another question.
yeah.
Are nanorobots used in chemotherapy?
Yes, the chemotherapy is a very hard therapy, right? What happens in chemotherapy is you have to externally do something. The nanorobots, you don't have to do anything, you just have to send it. The chemotherapy is a very harsh treatment actually, right? The chemotherapy is very harsh treatment, but in this one you are not it is non-invasive. Chemotherapy is an invasive technique wherein you have to do something, burn something, or like that, right? So chemotherapy is one of the treatment, but that chemotherapy is very expensive, harsh, and not an ultimate solution. What happens with chemotherapy is only at particular place wherever the cancer is, that part you can change. But in the cancer, the biggest problem is the virus is spread throughout the body. You can't keep on doing chemotherapy everywhere. That becomes very expensive. That's why the cancer is becoming very expensive, right? All this virus stuffs, even the AIDS virus, anything, because of their nanoscale, it becomes very expensive over the period of time to treat them. Okay.
Another question.
Yeah.
Any of the lab available in India for the manufacturing of nano FET?
Yeah. Actually, I will show you. We have much more facilities than anywhere else in all the CSIRO labs. That is, if you might have gone through. So that will be there. And I will show you some of the slide here. I just showed you initially. That's the reason that in Indian Institute of Technology, Kanpur, we have one of the National Center for Flexible Electronics. It has all the nano facilities available, whichever the world-class facilities. And all the defense labs are available. Indian Institute of Science, of course, is one of the, in Bangalore itself, we have very near to that. So even some of the new IITs are also coming up with these kind of stuffs. So there is a lot of scope, and many researchers are required actually. There are sometimes dedicated researchers are in very scarcity, because generally people don't try to be patientful and do that kind of research. So there are a lot of facilities back in India. It's a matter of time and search you have to do. And also sometimes what happens is the students generally go and think that if they compete and get very high gate score or something, then only they can go there. It's not like that. You don't have to wait for it. You can just go as a research assistant there with this some of these things, and they will be very happy to give you the facilities to work, I think so. So there are many universities all over the country spread out which are having this kind of facilities. India is very vibrant because our prime minister and all the government is also saying that because this is low cost and is very easily very easily formable, and it is very essential for our country that all this nanotechnology stuff grows. A lot of investment has been done by Government of India. Go
So,
to the website of Department of Science and Technology, Government of India. You will be able to find all the facilities.
now another question.
Yeah.
If AI robots come to society as a commercial purpose, will it be creating a lot of unemployment?
No, actually, there has no, that is a debatable stuff. I mean, that is of course a very big debatable issue, and there are a lot of TED talks on that particular topic itself. But my personal opinion is that we have to take any change with an open mind, and make sure and put the sufficient filters wherever essential, so that they will not be harmful for us who created it. So that has to go hand in hand, because but their importance is very high, because for example, now if I want to see something in back in Mars, what is happening, I would not like to send a human being, right? I would like to send a robot with an artificial skin which is made of nanotechnology, right? We want to see first, before we kill a human being by sending there, we want to send a robot with an artificial skin, or like to see how the behavior of that particular environment is on that skin, or on how is it in that mind. So robot will be essential, is essential, some like, so that like, but the always like every opportunity comes with its harm. So in this, the harm can be very big and drastic. So that's why the separate school of thought, like how to train those kind of things in ethical and a good manner, is a part of transdisciplinary research, which many departments all over the world, even in India, like IIM, because they are good in management. IIM people, management people, are interacting with the big of physicists. That's what Mr. Bill Gates, as you can see on the screen, was the same question was like how we can stop them. So that was essential. So, okay.
Yeah, sir. Another question: can
Yeah.
nanomaterials be used to accelerate tissue growth, resulting in speedy healing of cuts, possibly in surgeries and similar procedures?
Yes, yes. So what will happen is the tissues, when what happen in the, I'm not a doctor, but I know the basics of it, and because of my interest in this transdisciplinary research, I know the basics of it. Like what all the tissues are made of cells, right? All this basic cells and stuff. So whatever if that particular cell or the basic entity at the DNA level, if we are able to tweak it, then the possibility whatever is hindering them to not to grow, we can allow it to grow. Okay, so whether then completely new tissue can be born out of it is a completely different story, because we have to create DNAs and appropriately create DNAs. But the tissue growth which has hampered, yes, if we do proper research, and the people have been researching, and for example, John Hopkins University is pioneering in USA. It's an US university, one of the best ones in the medical field, research related to nanotechnology and robotics. So they are also doing the research on those kind of stuffs, wherein that kind in collaboration with other universities like MIT, that kind of stuff is possible if we properly tweak it. Okay, so but we can't because that is still in the research phase as of now. Okay.
Yeah. Another question from one of the student:
Yeah.
is nanotechnology a good career in India?
Yeah. Yes, of course, it will be a very good career. Nanotechnology is a very good career. Nanotechnology is, first of all, a multidisciplinary subject, because the moment you become a nanotechnologist, I am talking about robotics. I'm a nanotechnologist, right? So I can talk about robotics. I can go and give solution to the doctors. I can go and give solutions to the electronics industry. I can go and give solutions to the mechanical industry, because the mechanical is also becoming because the robots are very flexible now. If you go to a company called Boston Dynamics in USA, they have the robots which can jump and dance and run, right? So all that is mechanical properties are getting changed from nanotechnology. So any particular subject, if how much depth of passion you have towards that, ultimately matters. Of course, nanotechnology is one of them. It is not the ultimatum or something, but it is a transdisciplinary subject where only one knowledge is not sufficient. I think so you should always opt something where only one particular knowledge is not enough. The moment when you select something where multiple knowledges are used in your domain of work or interest, naturally the amount of opportunities which will come up will be very high. And also the nanotechnology for entrepreneurial people who want to start up things, because there is no need of very hi-fi fab labs like this. The moment only at the development phase this is essential, but we can print everything with our inkjet printer, which is there in the home, right? So those kind of printers. So anybody can start developing using physics. This one and 3D printing and all these stuffs. Of course, yeah, you should. These are one of the cutting edge the possible research fields. So you should opt if you have an opportunity.
Yeah, another participant, Mohan Krishna, has raised the hand. Sir,
Yes.
you can unmute and ask the question.
Yeah. Thank you, Mohan Krishna. Tell me.
Hello.
Yeah.
Mohan Krishna, can you hear me?
No, thank you, sir. Good evening, sir.
Good evening. Yeah.
Sir, regarding this nano, when we observe that bulk material to nano, when the size is reduces, the properties become changes. Is it, sir?
Yes. Yes.
Yeah.
Yes.
Can we find the properties of all the material is same for bulk material to when it converted bulk material to nano, or something is different? Can we draw any law for that? That's my first question.
Yeah, absolutely. We can draw a law like how it is changing.
Yeah.
From one phase to another phase, how is it changing? We can draw the conclusions, and that is how. Otherwise, that systematic variation from one scale to another scale when the material is changed, that is essential, right? So that is the basics of this. That is the basics of that.
Yeah,
so,
another, maybe it is a funny question, but please answer. If there is any other chance to reduce other than 100 nanometer the size of a
below 1 nanometer, you are saying?
Yes.
So that's where the graphene comes into picture, because what happens is the graphenes based material are two-dimensional materials. See, the even 100 nanometer, sometimes there will be a three-dimensional factor there. So people are working below for these 2D materials, which have an atomic scale, because atom itself is, right, 10 to the power of minus 10. We are, and nano is 10 to the power of minus 9. So we are almost near to the atomic scale now, right? So more smaller means how smaller? Like, I mean, yeah. So it becomes like we have already reached sufficiently, but still, if we want, then that research is also going on, and on the 2D materials, two-dimensional materials they call it, and you can explore about it. So the 2D materials are next big thing other than the nanotechnology. Yeah.
Okay. Thank you, sir.
Thank you.
Okay. Any other questions from the participants? You can unmute. Srinivasulu, sir, you can unmute yourself and ask the question.
Yeah, hello, sir.
Yeah. Please go ahead, sir.
Is it audible?
Yeah, sir.
Sir, this is Srinivas from JNU Hyderabad.
Yeah. Oh, hi.
Yeah.
Oh, Jane. Oh, you might know much better than all of them.
Yeah, thank you, sir.
It's a very good university. Yeah.
Thank you, sir. I have one small doubt, sir.
Yeah.
I completed my PhD in pure physics, like fiber optic sensor, my research area.
Oh, okay.
Is there any employability for in this field?
Yeah, actually, availability is there. It depends upon how transdisciplinary you are and how you approach the problem and write a project proposal, right?
Okay.
What kind of proposal you write? Like, for example, now if I want to get a scholarship back in Japan or anywhere, it's all about like what thought comes into my mind.
Okay.
How many this kind of lectures I attend, how many different possibilities I explore, and whom I contact. The moment you finish your masters, all that becomes is like whom we are in interaction with, whom we are contacting, and what we have in our mind. So, yeah, so there are opportunities are very high. It's just a matter of search, I think so.
Yeah. Okay, sir. Thank you, sir. Thank you very much. It is a very informative session.
Yeah,
thank you. Very nice. Thank you. Yeah, my pleasure, man. My pleasure.
Yeah, another participant.
Okay, sir,
yes.
Yeah, Irappa Ernal. Sir, you can unmute.
Hello, sir. Sir, I
Hello.
want. Yes, sir.
Yeah.
Yes, I have the doubt. What is what are the application of these nanomaterials to the superconductor?
Yes. So what happens is, as I had shown in one of the slides, the moment we bring it to the nanoscale, the electrons or holes, that is N-type or P-type materials, whichever are coming up, can be made as very highly conductive. or we can reduce the resistance and increase the resistance out of it by changing the bands. So naturally, the superconductivity concept is a completely different concept, because there we want to add nano. For example, if you see a MOSFET, right? What happens is, in the MOSFETs or like normal traditional electronics, we dope with extra electrons,
Yes.
extra holes and electrons. So, and we try to make it more and more and more conductive as much as possible. So superconductivity is generally that kind of phenomenon. But in the nanomaterials, they are using nanoparticles to aid the phenomenon of superconductivity. Okay, they themselves are used in superconductor is a different way of discussion, but generally nanoparticles are used to aid the process of superconductivity in order to make them more and more vibrantly conductive. Okay, so yeah.
Yeah, another
Yes,
question
exactly.
from Sonali Sinha Roy. Madam, you
Yes.
can just unmute yourself.
Yeah, so it was really a very informative session. Actually,
thank you
I'm
so much.
talking from Turkey. I'm a
Oh,
global goodwill ambassador, yes, and also an educator, but not in physics.
oh yeah.
I'm an economist. So my question particularly is, I was listening, and my question is,
Yes.
if it is so advanced, this
Yes.
technique, why are
Yes.
we not able to find a treatment for COVID-19? Because it is a
Yeah.
virus.
Yes. So this is a very good question. Actually, the fundamental problem is, because you are an economist, I will try to explain an economical answer for that as well. Because what happens is, until now, we were only aiding the doctors and engineers, not much to the scientists. The much of aid and funding was not there. So it was not at all. So the best of the best had not come in science. That is a fundamental problem. First thing is that. So now, when whoever people have come into the science field, they are trying to do their best. But why it is not a problem is the transdisciplinarity problem. What the proper interaction between the physicists, the scientists, and the doctors is not there. Also, why the other, that is the second point. And the third point is that the moment we change it on the human body, right, the moment we put it onto the human body, any change we are trying to create, yeah, any vaccine we are able to try to find, it might harm the human body drastically, which we have not known before. So proper, it is not that there is no medicine. They have already 15 to 20 people have come up with so many of the solutions to that. But whether it will be applicable to the human body or not, how once the moment it changes over 6 months, what will happen, we don't know. So that is the phase where it is. And the fourth point basically is that, see, the nano robots or the nano technology we can use, and we can find it out. So the sufficient funding, the moment the crisis comes, when we increase, this is not going to happen. The basic research, transdisciplinary research, had to be done before. Now it's a big learning experience, wherein that's where a lot of funding is coming up into this particular field, because this kind of crisis has occurred at the nanoscale. So I think so there is a lot of scope for that. And yeah, we can discuss about it as a subject, like why there has not been a medication to that. Because before concluding on that, I would like to say is that, see, they are not trying to find a medicine to that. They are trying to find a vaccine. So viruses generally don't have any medicine. Viruses always have a vaccine. Vaccine means it should not come from next time. Medicine means, oh, whatever has come to me, I will solve it, right? I will make it go. So there is a two different thing, finding the vaccine and finding the medicine. So now all the research focus is on finding generally the vaccines. So when you find the vaccine, it has to be a long-term solution, because we are going to put that vaccine on all the people. And the moment if some drastic change happens on all the people, it might be adverse impactly, and the whole situation might go wrong, because at nanoscale, if you put something, we don't know what actually happens. So the lot of trial and error has to take place. So that's what is going on from some of the elite institutes of the world. Yeah. So I hope some part of the question I answered.
Yeah, thank you, sir. Another participant, Paramesh Gantasala, has raised his hand. Sir, please
Okay,
go
yeah,
ahead,
sure.
unmute yourself. Please go ahead.
Hello, Paramesh.
Hello.
Yeah, please tell me.
Yeah, Paramesh Gantasala, sir. Hello.
Yes. Yeah.
Sir, you can unmute yourself.
Thank you for all in the chat who said the session was good. I'm very thankful
Yeah,
to
we
all
are
of you for
getting
that.
very excellent feedback on the session.
Oh, thank you.
People
Yes.
are going crazy about this nanorobotics. And
Yes.
yeah, any other question? Another participant by his nickname TPK. You can unmute yourself. Hello. I think okay, sir. So we can.
Okay.
Yes, sir. Hello.
Yeah. Some question coming in. Yeah.
Yes.
Go
I
ahead,
am
sir.
Yes.
Sita Ramarao, sir. TPK. I'm using my wife's laptop. That's why it is coming like TPK.
Okay, sir. You can go ahead with the question. Yeah.
I am Dr. Sita Ramarao, sir. Sir, I am a professor in the mechanical department. What is the effect of the properties by using nanomaterials in the composite structures? That is my question.
In using those nanomaterials and nanostructures into composite?
Yes, sir. So what
On
kind
the
of usually change? Like hardness or conjunctions?
you are not audible actually. So
mechanical properties, how they are changing? That is why I'm thinking.
Yeah, I showed you the mechanical property. The first mechanical property is it becomes highly flexible, right? The moment we change at the nanoparticle scale and we are able to make inks out of it, right? The moment we make ink out of it, previously there was no such ink which was made out of the material, right? The conductive material based ink. For example, if you see any 3D printed device, in that there are no wires anymore. The wires are printed by using an inkjet printer. So the mechanical property as such will change because because anything on the surface can be printed, right? So the mechanical property of the material will change. The mechanical property of the device on which it will be printed or used will be a different, right? So definitely the moment we change the size, it means the mechanical property has defaultly changed there, right? On the nano composites, again, similar to the conductivity, for the nano composites, the moment we go at the nanoscale, the properties which will be more feasible for us will be exponentially tuned by using nanoparticles. Okay.
Thank you.
So that is we can discuss separately on that.
Okay.
In more detail.
Okay. Thank you, sir. It's a wonderful session. Now, I hand over the session to Srimati Puranik Madam to give a vote of thanks. It was indeed a wonderful session. Over to you, madam.
Thank you, sir. Good evening to one and all.
Thank you for all your messages in the chat box.
It gives me an immense pleasure to propose vote of thanks on behalf of KLE Society's management, principal, IQAC, Department of Physics, Electronics, and my own behalf. I would like to express my heartfelt thanks to today's guest speaker, Dr. Basangoda Patil, team leader, R&D Technologies, Queensland, Australia, for sparing his valuable time and enlightening us with very good information about nanomaterials and robotics. Thank you, sir.
Oh, thank you so much.
Thank our beloved Dr. Vivian sir and Vice Principal Dr. Srimati Jaya Madam for supporting and giving us an opportunity to organize this event. Thank you, sir and madam. I would also thank the organizing committee members, that is IQS coordinator, convener, and organizing secretary for organizing this event. I also extend my gratitude to all my colleagues for their technical support and assistance. Last but not the least, I also extend my thanks to all participants without whom this international webinar would not be successful. Thank you, everyone and all.
Yeah, thank you, madam. Thank you, sir. It was indeed a wonderful session, and it was a proud privilege to have you on this session. So thank you so much.
It was my pleasure as well to interact with so many people, and thank you for all the people who have sent the messages in the chat.
Yeah.
Nice.
Thank you, sir. So with this, we conclude the session. One information to the participants: the feedback link is provided to your registered email ID. Please check back in your emails. The link is provided. There you can submit the feedback form. After submission of the feedback form, the certificate of participation will be sent to your registered email ID. Thank you so much for being with us for this entire session and making this event a grand success. Thank you, one and all.